but I think we're there. So what we're going to do today is the first lecture period, roughly speaking. I'm going to finish off this slide set, looking at different logic styles. So this is the slide where we left off. Then we'll have a pause, as usual, for a few minutes. And then after that, we will go through the tutorial. And hopefully you've had a chance to look at it. I think there's one question we hadn't covered, but the rest you should have been able to make a good attempt at. So let's go through this slide. So what we were looking at the end of the last lecture was pre-charge logic, and we looked at the way that pre-charge logic saves space so that you don't need to have both the N block and the P block. You just simply have either an N block or the P block, and you have two clock transistors instead of the other block. So what we're going to look at here is a cascaded set of two gates. So the very simple gates using pre-charge logic, there's going to be two inverters. Now, you know what an inverter looks like in regular CMOS. There's a single NMOS transistor and a single PMOS transistor. So the N block and the P block are just a single transistor. So when you put it into pre-charge logic, what you end up with is your clock transistors here and here, and your inverter now is your single NMOS transistor. Okay, so if you remember that the way pre-charge logic works is that the clock needs to cycle from low to high, and when the clock's in the low phase, then you are pre-charging the nodes, and then when it's in high, it evaluates. So that's what we've set up here. We've got two inverters cascaded together. So what you'd expect to happen, and what you'd want to happen with two inverters, is that if you had a high signal, for instance, coming in at A, then X, which is the intermediate load, would be low, and then Z, which is the final node, will be back to high again. So that's what we're looking for. And what we want to see is what happens. And the thing that makes it slightly dodgy here is what we've seen before already, is that you can have capacitances in these various nodes, and these can cause issues. So looking at the timing diagram here, what you can see is in the first phase, in the pre-charge phase, everything is exactly as you would expect and want. So the clock is low for pre-charge, nodes X and Z pre-charge high because they're being pulled high through this P transistor here at the top, this clock, and this clock, also low, isolates everything from the ground. So everything looks as it should do when you're at the pre-charge stage. Then when you enter the evaluation stage, these transistors switch off. These transistors here switch on. So what happens? Well, of course, the switch isn't instantaneous. So we're approximating the switch as a nice trapezoidal form. And at some point, the clock passes the threshold point in the middle. And at that point, X will begin to fall. And X takes some time to fall. So to get from the beginning of X falling to when it gets to the threshold, that takes a certain time, delta T. But all the time that X is high, you've got a high signal coming into this transistor here. the second of the two inverters. And of course, if you've got a high signal there, it's going to generate a low at the output Z. Now, it's only high for a very short period, but if it's high at all, Z will start to fall. So what we can see is that some charge will leak from Z to M and Z falls. It's obviously going to be a problem. Now, obviously, if delta T is big and if the capacitance of the node at Z is not very high, then it's going to fall more. So you can eventually get a situation where Z is misevaluated to a low. So pre-charge logic has a problem. If you connect one piece of pre-charge logic to another, and if the output of any of the gates is falling, then because initially it was high, which is only high for a short period, but initially it was high, that means that the next gate initially has the wrong input, and you can get an output that's incorrect. So there are two ways this can be fixed. So the first one we're going to look at is domino logic. And what I've got here in my diagram is basically the same things we had before, except for two things. One is I've replaced the fact that it's a single inverter with a whole N block. So this really applies to any gate. It doesn't have to be an inverter. An inverter is just nice and simple to think about. But basically, if you've got an N block, which is what you'd typically use for pre-charge logic, an N block, if you've got an input to an N block that's high, the N block tends to have a high output. If you've got an input that goes low, that doesn't necessarily, but it could mean the N block goes low. Okay, so it depends what the N block is. So we've got two N blocks, but the other thing we've done is we've put an inverter in the middle. Now, with that inverter, if you've got a falling signal here at X, that then corresponds to a rising signal here at Y, and that doesn't cause a problem to the next N block. So you don't get that same problem with the misevaluation. And you then can have a whole series of such gates in a row. Because of the time delay with the inverter, so it's not a big time delay we're talking about, but there is a time delay. This gate will evaluate first, and then this gate will evaluate, and so on. Okay. In case you're worried about it, if you think about it, if the logic went the other direction, and you might think, well, what happens if this was rising, because this would then be falling. But that's catered for by the fact that the pre-charge pre-charges all these nodes high anyway. So that doesn't, in the end, cause a problem. So domino logic is essentially you're putting an inverter in between every block, and that is one way of fixing the problem. The other way of fixing the problem is so-called zipper logic. And here what we do is we alternate N and P blocks. So if you remember with pre-charged logic, we would generally use pre-charged logic with an N block, because N blocks typically are smaller than P blocks. But you can also do it with a P block. So if you alternate your N and your P blocks, you then have to make sure your clocks are set correctly. So because the P block, everything is the other way around, you need the inverse clock here and here, and this is the pre-charged node at Z here. But essentially, because P block logic is the inverse of N block logic, a falling X will evaluate correctly. And the whole system will again work. So you can have an N block followed by a P block, followed again by another N block. So that's another way which you can use pre-charged logic. Pre-charged logic, by the way, is still used. It's had its heyday, really, I suppose, if you look back about 20 years ago, when companies were trying to get the maximum out of microprocessors in terms of speed. Obviously, still trying to get speed, but the emphasis now is more on making lots and lots of cores. And pre-charge actually is quite tricky to use, so it gets used mainly in niche applications. The CMOS logic, which you looked at first, is generally the first go-to type of logic. But having said that, these other ones do exist, and we look at them because, as I say, in niche applications and certain types of gate, they are useful. So the next one we want to look at is a pass transistor. So what's a pass transistor? What we're going to do is we're going to look at a transistor and turn it round. It doesn't stop it being a transistor, but think about a different way of passing information. So what we're going to say is, can we have an information flow from the source to the drain, or drain to the source? It doesn't, it's a symmetrical device, so it doesn't matter, which is controlled by the gate. So you can imagine that if you turn the transistor on, a signal will flow from in to out. And if you turn the transistor off, then it won't. So the question is, can we use that as a form of logic? Now, since the signal is passing from the input to the output, the source to the drain, then VS and VD need to be roughly the same. Okay, otherwise it's not going to work. So if you've got VS and VD roughly the same, and less than the gate voltage minus the threshold, then you're in linear mode. When will it conduct? Well, it will conduct when VG is high at VDD, so that's fine. And then NMOS, the gate at VDD, it'll start to conduct. So let's think what happens when we sweep the input voltage. So as you sweep the input voltage, VS increases, and as a consequence of VS increasing, the voltage between the gate and the source will decrease. Okay, and eventually, when you get, okay, take right to the extreme, if the voltage VS reached VDD, so you get right to the supply rail, then VGS is going to be 0. And we know that VGS is 0, the transistor won't conduct. And in fact, if the voltage difference is within one threshold voltage of VDD, it won't conduct. So you can imagine that the impedance of this device is just going to go up as the input voltage goes up. We can do some maths on that if we like, it's not too difficult. So the impedance is just simply going to be dV by di, differentiate. we know the equation for the current in this mode. So what we're going to do, because we've got the current equation, we're going to find di by dv instead of dv by di, and then just invert it. So if we differentiate this, it's fairly straightforward. Now in the limit, just to make life easier to see what's going on here, we're going to say VDS is going to be roughly 0. So this term vanishes. And if we invert this, we end up with this free impedance, which is essentially a 1 over x type equation. Z equals 1 over v, except there's an offset of the threshold voltage. And so it looks exactly like we saw on the previous sketch. So when the input voltage Vs is 0, then the impedance is low, and it works really nicely. As the voltage goes up, the impedance goes up, so it doesn't work so well. So we can only use the NMOS for somewhere below VDD minus V threshold, and probably quite a bit below that, because otherwise it gets really slow. So what we can do is we can say, well, the NMOS passes the 0 quite nicely. If you put a signal of 0 in, you get 0 out, and the impedance is low, and that's great. So if you use the PMOS transistor in parallel, it will pass a 1 quite happily, because all the voltages are inverted. So if you draw that little diagram with the impedance, the NMOS impedance goes up. PMOS is exactly the same, but the other direction. And then, of course, because you put them in parallel, the total impedance is just this at the bottom, which is good at either end and so-so in the middle. So these pairs of transistors will form what's called a transmission gate. So basically, you've got two pass gates. So a pass gate would be a single NMOS or single PMOS, but you put two together, we call it a transmission gate. And so you can see that here in this diagram. You've got a PMOS pass gate here, you've got an NMOS pass gate here. If you put them together, you end up with a transmission gate. And transmission gate can pass both zeros and ones. What you have to note is that the control voltage is opposite for the two gates. So you've got a 1 on the NMOS, you need a 0 on the PMOS, which means, of course, you need an inverter to make the thing work, to invert the control. So essentially, if control is 0, it's high impedance. If it's 1, it just passes. And that's a really useful feature. So it's got its own symbol, which looks like this. So the symbol looks a little bit like two amplifiers facing opposite directions on top of each other, except there's no amplification in this situation. Okay, so we've got a transmission gate. The question is, can we do anything with it? It sounds like it might be useful. What can we do? So here's some basic logic gates which we can make with the transmission gate. So what you'll notice there straight away is that with the standard CMOS logic, everything was inverted. You had NAND and NOR and so on. Whereas here, we've got AND and OR, so it doesn't invert. So we can have an AND gate, an OR gate, an exclusive OR gate. So I'll go through one of them in detail, and I'll leave you to work through the others just to convince yourselves that they work. So if you look at the AND gate to start with, how's that going to work? Well, the thing to notice is that the two transmission gates are wired up in the opposite directions. When I say opposite directions, this transmission gate has a B and a B bar. So B going to the NMOS and a B bar going to the PMOS, whereas this one has a B bar going to the NMOS and a B going to the PMOS. So what that means is that either one of the transmission gates is on or the other one's on, they're not both on at the same time. So let's take the case where B is 0. So if B is 0, then this top gate is going to be closed and this one's going to be open. And so the output's going to be, whichever B is going to come through to Z. So of course, no, that's wrong, sorry. I'm looking at it thinking that's not going to work, and it won't, because if B is 0, then B bar is 1, and you've got a 1 coming to the NMOS, so that bottom one's open. Okay. So if B is 1, this is open. B comes through, so if B is 1, you get Z is 1. If B is 0, you get Z is 0. Then if you put B is 0, then you've got a 0 coming to the NMOS at the top, so the transmission gate is closed. With myself, it's easy to draw a truth table, sorry. If B is 0, this one's closed, is that right? You need to help me here. It's always harder to do this thing when you're standing in front of a crowd of people. Excuse me. So B is 0, this is closed, this is 1, is that true? B is 0. So that would say that you get a 0 here, whatever happens. Okay, so if B is 0, you get a 0 at Z, whatever happens. Okay. If B is 1, then this one opens and A comes through. And if A comes through, then if A is 0, you still get a 0, and if A is 1, you get a 1. So the only time you get a 1 is if they're both 1. Okay, sorry, it took me a few moments to stumble there, but I think that's it. So it's not that difficult. You just need to keep a straight head and work through. The OR gate is pretty similar. Just the wiring is obviously slightly different. So you get the OR functionality, and the exclusive OR also works. What you'll notice is that the exclusive OR with CMOS was quite complicated. It needed a lot of gates, whereas here, the exclusive OR is working with not so many gates. So that is one definite advantage for this type of gate. So in principle, all designs can be implemented with N or P pass gates only. And you need, this is again, where N gets meaning two different things in two different sentences. You need 2N plus 2 gates. So, okay. So how many transistors do you need? Well, if you look at the number of transistors you've got here, you've got 2 transistors to make this transmission gate. You need 2 for this transmission gate, and you need 2 for the inverter, because you've got a B and a B bar. So you need 6 transistors. So you've got 2 inputs, you need 6 transistors. So it's 2N plus 2. So if you had 3 inputs, so you wanted to do an AND with 3 inputs, you work out the circuit diagram, you would need 3 times 2 plus 2, which would give you 8 gates. Which that turns out to be exactly the same number of gates as you use for CMOS. Another thing you can do with the transmission gate, which is quite nice, is to make a multiplexer. So a multiplexer will choose one value out of many. And because of the way the transmission gate works, either letting a signal through or not, it becomes really quite straightforward to make a multiplexer. So here we are, it's a simple multiplexer with 2 inputs, A and B, 2 bits. So, and we're looking at S here as our signal, which is going to choose which one. So if we choose S equal to 1, we get A. because this transmission gate is open and this one's closed. And then if we choose S to be 0, then this is closed, this one's open, and we end up with B. So it's a simple multiplexer, and it's relatively easy to scale that up to as many bits as we like. So multiplexers are something which Fastgate is good for. So it shows that transmission gate. What's the drawback of a transmission gate? So it looks quite nice, but the basic difference, or one important difference between the CMOS logic and transmission gate logic is that with transmission gate logic, you start losing signal as you go through the logic gates. With standard CMOS, every time you go through a gate, the output is pulled strongly either high or low. So you're regenerating your signal at every stage. Whereas with a transmission gate, it's just going through a transistor or transistor pair, and it will lose some signal because you're going to get some IR drop, some impedance to the transistors. So that means that if you want to have a whole series of logic gates, you will every now and again need to have some regeneration. And so a typical way you might do that is you've got a couple of blocks of transmission gate logic, then you put in an inverter, which of course regenerates the signal, and then you can have some more logic there. And if you think about the timing for these, which I'm not going to go through explicitly, but you should be able to work out the equations for yourself, we can essentially view the transistors in the transmission gate as having an impedance. We looked a bit at that a couple of slides ago. There's going to be a capacitance associated with each of the nodes and also with the wiring. And so basically it just looks like an RC delay from one to the next. And then you can calculate delays, and you can calculate how the signal will drop and how frequently you need to have your regeneration. So we've looked at CMOS, we looked at pre-charge, we looked at transmission gates. So the final logic style we're going to look at is C-squared MOS, or clocked CMOS. And what we'll see is this has similarities with all the ones we've seen up to now. Okay. So again, I'm going to start with an inverter as a nice simple example. So it's a clocked inverter. So let's look at the circuit. The clock is our signal C here. And essentially, what it looks like is that if we've got our inverter, which is this D input coming in here and here, and there's the output Q, which would be D bar. If we didn't have the pair of clock transistors, that would look exactly like a standard CMOS inverter. Okay, you've got your NMOS, you've got your PMOS, and the outputs in the middle. What you'll also notice is that the clock also looks a bit like an inverter. It's got a NMOS and a PMOS, and between them, you have the output. And the way this works is that when the clock is 0, the whole device goes into a high impedance output state. So you can draw a little truth table here. So let's think about that. So if you put the clock to 0, then this transistor is turned off, and this transistor is turned off. And that means that the output Q is isolated from both the ground and VDD, and therefore it's high impedance. So if the clock is 0, doesn't matter what D is, you've got a high impedance output. If the clock is 1, then what happens? Well, the clock's 1, both these center transistors are switched on, and then the outer logic blocks, which in this case is just single NMOS and a single PMOS, the outer logic blocks just work as normal. Okay, so when D is high, you'll get low in the output, and when D is low, you'll get high in the output. It just works as a standard inverter. So sometimes referred to as a tri-state inverter because it's got 3 states now. It can invert, so either get output of 0, 1, or high impedance. And if you're looking at the names of the terminals D and Q, it should possibly remind you of a latch, and this device indeed has a latching operation. It also has, and we'll look at the application for latches in a few minutes. It's also got similar properties to a transmission gate because of the high impedance state. But also, like CMOS, it gives you a full rail-to-rail output, so it regenerates the signal. So it's got lots of good things about it. And like all circuits, it's got its own circuit diagram. So it just looks like an inverter with a couple of control signals coming in, C and C bar. Now, first thing I want to look at is, does the clock need to go in the middle? Because this device here looks pretty symmetrical. And is there any particular reason why you should put the clock in the middle, or could it go on the outside and put D on the inside? And would the device work just as well in that situation? So I want to think a little bit about that next. So here we are. We put the clock next to the power rails. We just switch them around. And nominally, it's got exactly the same function. So if you go through it, if clock is 0, then the whole center of the circuit is isolated from the power supply rails, and Q is just going to float. And yeah, if clock is 1, then the inverter just works as normal. The thing we need to think about here is charge sharing. We've seen charge sharing once or twice before, and here it becomes important as well. So you've got this situation here. Suppose the clock is off and you toggle the input D. Then what happens? Well, we've got 3 nodes we need to think about. We've got the output, which we're obviously mainly concerned about. We want the output to be either 1, 0, or high impedance. But we also have to consider nodes X and Y. And when the output is in the high impedance state, we're usually relying on stray capacitance or input gate capacitance to keep it in the state it was in before. Okay, so although it's a high impedance state, it's not just the fact it's high impedance that we're concerned about. We're also concerned whether it used to be a 1 or a 0, and we should stay at 1 or 0, at least for a period of time until the charge leaks from the capacitor. But if you have the clock at 0 and you toggle D, then, okay, take a rising D, N turns on, P turns off, and charge will flow from Q to Y. And so the voltage at Q will drop. And if you went the other direction, you'd have the same problem in the other way. So basically, because of charge sharing between these nodes, if you put the clock at the outside, then although the output is high impedance, it doesn't hold its value terribly well when D toggles, and that's not good. So putting the clock in the center removes that problem, and it's the way we go. So, okay, we can have our C squared MOS inverter here, and then we simply add a regular inverter to make a half latch. So the capacitance that's shown here is not an extra capacitor, that's just the capacitance of the input gates to this inverter here. So this is called a half latch, sometimes a level sensitive latch or a transparent latch. So essentially where it works is that when C is high, C is 1, then Q is just D. The signal here just comes straight through, which is where the idea of a transparent latch comes from. It's transparent, D shoots straight through to Q. When the clock signal goes to 0, then Q is held. Okay, so it doesn't matter what happens to D now. Whatever voltage was stored in this capacitor just stays there, and Q is held. So you've got a latch. So remember what D used to be. So it's sensitive to the level of what D was before. Now, the memory here, you'll notice, is due only to stored charge. So it's not going to stay forever, but it will stay for some time. So it's called a dynamic latch. But we can actually use positive feedback to turn it into a static latch, which actually keeps the signal there. And that's relatively straightforward. So here's our dynamic latch, our dynamic half latch. If we add another inverter, as shown, then what happens? So this feedback will mean that if X was high, Q is low, and then of course this inverter will take that low signal and make it high, and because that inverter has gain, it keeps X high. So this can stay in its setting forever, right, as long as the power supply remains on. So it's a static design. What you do with the design here is we'd make the widths of the transistors in the keeper much smaller. So it would be a weaker inverter. Only needs to be strong enough to keep the signal at signal at X fixed. It doesn't need to be stronger than that. And the problem, of course, comes when you try and change D. So if the clock was 1, D changes, then the signal at D is competing with this inverter here to make the switch. Okay, so static latch is good from the point of view it keeps its memory forever, but because it's got a situation where you've got inverters competing against each other, I know we've made this one smaller, but it's still non-negligible, it makes it slower. So it's slower than the dynamic design, but it has the advantage of being static. Okay, so in summary, the C-squared MOS has the advantages of CMOS. It's full rail-to-rail operation. It's got gain. You can put any NMOS or PMOS block here and here. So it doesn't need to be just an inverter. Okay, you could use it for a NAND gate, NOR gate, or any other gate you wanted to use. You could put the correct blocks here and turn it into C-squared MOS. So you can use it for complex gates. It's useful for making things like latches. And you can make a full latch or an edge-triggered latch by putting half latches together. So if we put these two half latches together, okay, so we've got a half latch here, there's another half gate latch here, then this is a full latch, and essentially it now works that you don't get shoot through from D to Q. So when the clock is 1, D will go through to this intermediate node here. Then you switch the clock, and then this node is protected from D, but this opens up and the value here comes through to Q. And this change happens on the edge of the clock signal. So when the clock changes from 0 to 1, whichever value moves through. So it's called an edge triggered latch. You can also actually make latches using transmission gates. And so again, you can make a dynamic latch. You can do it like this. So that should be fairly obvious how that works. So when the clock is 1, D will move through to here. When the clock is 0, it won't. So it works very similarly to the C-squared MOS latch, apart, of course, from the fact it doesn't have any gain coming from here. So the signal driving has to be from the previous gate. You can also put a keeper on it, make it static. Another nice thing you can do with the transmission gate latches is that you can put another transmission gate here. And that essentially can be used to turn the keeper on and off as appropriate. So the idea is that when you're changing D, this one's open, but this one's closed. So the signal comes through here. This is closed now, so you don't have the feedback. So you're not fighting against the feedback, so it helps speed. And then, of course, when you close this, and this is having to be held by capacitance, by stored charge, then this opens and you get the feedback to keep it working. So that gives you a nice advantage of a static latch, which can actually go faster. As you can see, there's lots of ways you can organize these different logic styles together to make different devices, and ways you can make better devices. So if you look in textbooks, you will find lists of lots and lots and lots of devices which people have made over the years trying to improve the circuits and how you can make them better. So I'm just giving you a flavor here because we haven't got time to go through everything in detail. So, okay, more multiplexers. So we can use C-squared MOS as well to make multiplexer, as here. So we've seen this one already. Because the C-squared MOS has the tri-state, so it goes into higher output impedance, you can essentially do exactly the same thing, and you get a multiplexer. The one difference here is, if you look there, because this is an inverting gate, you're selecting A invert here rather than A here. So this multiplexer inverts at the same time. But otherwise it has the same functionality. So from the design point of view, we said some lectures ago that the only thing that the designer can change about a transistor is the transistor width. But when it comes to designing circuits, of course, you've got a lot more choice now, because, for instance, you look at these two different implementations of a multiplexer. Well, this has got fewer transistors, so it's easier to lay out, fits in your space easier. On the other hand, this one's got gain, it's safer, and therefore you've got a choice. What's more important in your final chip which you're making? And you then have to start, working out whether space saving is more important, or whether actually the cost isn't so critical. What you want is that the device works. Is it a device to make a cheap toy, or is it a device to guide a spaceship? There's different implications for the types of uses for a device and how you would go about designing it. So dynamic and static, we've seen this already. So we know that dynamic is faster, tends to have fewer transistors, you need to add keepers and so on to make things static. It's got reduced input capacitance because it's got fewer transistors. So again, it makes it faster and helps power consumption, but you can't idle it. It doesn't maintain its value. Static can idle indefinitely. So they're different and useful in different situations. Okay, so we've looked at standard cell libraries. We didn't go in any detail, we just saw that they existed and that there's many gates there supplied by a wafer fab for the designer to choose from. So it provides a large coverage of lots of gates, not exhaustive, because not every single gate we can ever think of, but it's a good selection. And from the designer point of view, we need to bear in mind trade-offs such as speed. Is speed important? Safety versus risk, reliability there, power budget, all these things we need to think about. And yeah, we haven't accounted for all sorts of other issues, such as the design time. If you want to get your device out quickly and sell it next week rather than next year, sometimes it's better just to use things off the shelf. So from the design point of view, that would mean using the standard library, whereas you could say, well, if I took a lot longer to design it and made my own custom gates all the time, it could be better, but it might take twice as long to make, and that has cost implications too. Floor planning is something we'll look at a later date. Oops, sorry. So here's the summary of what we've looked at, different logic styles, so NMOS, CMOS, C-squared MOS, pre-charged pass gates and transmission gates, okay? Maybe your head's buzzing with all these, but if you go back and look through the lecture, hopefully these are more familiar to you, at least the words. And then just a summary here. Do they have static power implications? Well, generally speaking, no, apart from NMOS. How many transistors do you need for N inputs? So some of them need fewer, some of them need more. speed information and so on. Okay, so what we're doing next is the tutorial, which we'll do after you've had a 10-minute break. So